Okay, so last time we did SAT, we were going to keep obviously building on that. We're going to talk about two particular problems, 2SAT and max 2SAT. We talked about it a little bit at the end last time. Let me just quickly recap. So we talked about SAT, right? So just these Boolean formulas, so on and so forth. The big question, right? The problem is I give you a Boolean formula, and you want to tell me if there is a satisfying assignment. Okay, and the big question is there an efficient algorithm for this problem? It would be fantastic if there was. And the amazing thing is we don't know, right? Maybe one hint, for example, is that Boolean formulas are pretty expressive. Yeah.
But are you allowed to say the answer is yes, but not give a construction?
Well, you have to be correct though.
Is it possible that there's an algorithm that allows you to decide yes or no, but doesn't actually give you the
okay, here's actually a great question. Okay, let's do that. So, suppose you had a black box, okay, that given a SAT formula, it just spits out yes or no. So the question is, would it be okay if the algorithm just answered yes or no and never even provided an assignment? Would that count as a good algorithm, or would that meet our requirements? So, let me suppose you had a black box that can only answer yes or no correctly. I'm claiming that you should be able to actually get an assignment. Okay, so you have a black box, you can give it a formula, and let's say it says yes. Not great, so there is an assignment. How are you going to figure it out? Yeah, anyone?
You could you could look at the first variable, say, okay, let's try the case when it's true, substitute true everywhere, and then try it. If it works, then you could say, okay, we can assume it's true. And otherwise, we know that it must be false. And then we move on to the remaining x2.
Yeah, perfect. So let's plug in x1 equal true. That's some remaining formula with n minus 1 variables. And then plug it back into the box. Is this formula still satisfiable? If it says yes, you can keep going. If it says no, it's like, oh, x1 equals true was the wrong guess. I'll try x1 equals false. It should say yes, and then you can try out this x2. So in fact, they're closely linked. If you can actually answer yes or no, you can construct the solution. It's an okay answer, right? Okay, good. That's often given as a homework problem, but whatever. Okay, so SAT is very expressive. So that might actually tell you that getting a good algorithm might be too good to be true. I mean, I guess if we have AGI, anything's fair game, but still, just kidding. Okay, so then we started talking about more special cases, right? If we can't do much with Boolean formulas, what about something like something in CNF form or 3SAT, stuff like this? And what we showed, maybe it wasn't surprising by end of class, but might have been surprising a priori, which is that we also don't know if there's an algorithm for 3SAT. That's not maybe too surprising. But what we can prove is that there's an efficient algorithm for 3SAT if and only if there's an efficient algorithm for any Boolean formula. Yeah, and then the trick was that, you can actually do this assignment thing and break things down. Right, so this restriction to only 3 variables per clause actually isn't that big a deal. It doesn't actually reduce the generality of the problem. Okay, so in that sense, we kind of didn't make progress, but we also made some progress. We actually understand the problem better. Circuit SAT, same kind of story. Circuit SAT is just as hard as everything else. Okay, so that was where we left off. Well, kind of left off. We left off with 20 minutes left in class. So we started discussing a little bit 2SAT. So I'll just briefly review. So 2SAT, the only difference now is you only get 2 variables for every clause. Okay. Is there a polynomial time algorithm for 2SAT? That's one of the questions we'll address. The other question is max 2SAT, same input, but your goal is to maximize the number of clauses satisfied. Okay. Given this formula, what's the maximum number of clauses you can satisfy? You can turn that into a yes-no question by saying, is it possible to satisfy 10 clauses in this formula? Is it possible to satisfy 20 clauses in this formula? Clearly, if you can do this yes-no question, then you can get max, right? How?
You just keep trying to see where it goes.
Yeah, or a little more efficiently, you can binary search for the largest value, k. Can you get k clauses in this 2-set? So they're kind of similar. Okay, and then we took a poll. There's a few more of you, I think, last time. But, and these were the same numbers as before. So for each of these problems, you can decide if you think there's going to be a polynomial time algorithm, or if it was going to turn out to be just as tough as the Boolean formula stuff. Okay, and so the feeling was that for 2-sat, more of you thought it was going to be tough and hard, and then for max 2-sat, you thought it was more likely to be easy. Yeah, which is kind of reasonable, but as was pointed out at the end of last class, if you can solve max 2-sat, then you can solve 2-sat. Yeah, so so it sort of didn't make a lot of sense either, but that's okay. Does anyone want to revise their vote? Okay, so basically like 3. Okay, we'll do it quickly. All right, who thinks that for 2-sat we'll get a polynomial time algorithm? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then who thinks it'll still be hard? 1, 2, 3, 4. By the way, if we make the same mistake twice, I'm going to be a little disappointed, but not too disappointed. Like a little. Okay, now let's do max 2-sat. Who thinks we can get an algorithm? Oh, okay. None? And then who thinks it's going to be hard? 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that makes sense. Okay, good. All right, so this is actually a little more sensible than before. Okay, good. All right, so we are first going to try to do 2-sat. Okay, so all right, so I put 2 formulas up there. Okay, they're pretty similar. I think the second one just omits one of the clauses from the first. So is the first formula, is it satisfiable or not? I think we've seen this example before. No, it's listing every possible pair. So no matter how you set x1 and x2, it's going to make one of those clauses unhappy. Okay. What about the second one? Yeah, how? X1 is false and x2 is true. Looks like that works. It definitely works. Okay, good. All right. We're going to try to come up with an algorithm for this. But any ideas? We're going to try to come up with an algorithm to solve 2-sat. You have many stages where you can come up with ideas, but here's the initial stage where you have no hints. And you just want to see if you come up with anything.
There is only so many different kinds of Boolean formulas or expressions that only have 2 clauses, so we can maybe try to think about what they are. Like, I guess there's...
Okay, so
I guess, for example, if we have... Like, we can kind of deduce things like x1 or equality or things like that about any 2 variables and kind of like make assignments.
Yeah, so okay. So first, is there in fact a very small number of 2-sat formulas even like possible? That was one.
Or no, I mean for like any singular clause.
Any singular clause? Single clause?
For things which are possible.
Uh-huh. I agree. But 3-sat would only have 8. So it doesn't seem like that big a difference in that regard. Yeah. Sure.
Maybe do something where we like sub in 1 and then call the algorithm on the smaller.
Yeah, can I just try setting x1 to be true and then looking at the rest?
Yeah.
Well, okay, so if I set x1 to be true, and that would, well, okay, there's only two variables here, so it's not super interesting. But okay, so let's say you do true, and then well, at least at the very least, you can like do some kind of recursion, right? So let's say n is the number of variables. So, and let's say that like, I don't know, the total size is m, roughly. Whatever, roughly processing the whole thing will take time like O of m or something. So it feels like in that kind of algorithm, you try guessing 1, and you're going to have to spend like Tn of -1 time, plus maybe m to just like plug things in and rebuild your thing. But you might guess wrong. So it feels like there's that 2 Tn -1, which at least if that's just the algorithm, we can't leverage anything more, is going to look like 2 to the n plus some m. Yeah. Either one.
For each variable, you can see like it being true satisfies which clauses, and try to see like what the overlap between different variables.
Yeah, I mean, again, these examples are so small. Okay, let's see. Okay, how about this? Let's work through. I think this might be kind of similar. So, like, how do we okay? So it is true that how do we deduce that this formula is impossible? In this case, you can actually just see that all the clauses are there, and there must be some contradiction. I mean, I chose sort of a compact example, but this could have been a more general formula, and we're claiming we could come with an algorithm that figures out if it's not yes or no, right? Sorry, yeah?
Can we do the 2 to the n thing with like hash answers?
Oh, can you do 2 to the n but cache your answers? So what happens if you cache your answers? Well, how many possible problems are there?
For each variable, you have specific options. So you could have like some 3D state where you have some configuration of yes or no for each variable, and if you know that a subset evaluates to false, then you can't transition to that.
Sure. But if you have a problem that's parameterized by yes or no for a bunch of variables, I've already set x1 to be true, I've already set x2 to be false. How many problems are you going to get?
You're going to get 2 to the n.
You're going to get 2 to the n.
We have like some BP and 0 1 where like 0 is false and 1 is true for that variable, and we do like n transitions for the thing.
So in DP, it's like how much, sorry, my contact's calling me. How much history do you have to kind of remember, right? Like in that algorithm where I have to remember that I said x1 to be true and x2 to be false and x3, because that tells me what remains. And I need to remember all of them as far as I can tell. So it feels like if I'm just k steps in, I need to remember one of 2 to the k bits, so that's 2 to the k combinations. So one thing sneaky about DP is, in fact, it's very interesting to compare when DP works where it doesn't, right? Well, DP seems to solve everything, right? You can do American and American, the longest sequence, the super sequence of a palindrome, right? So but somehow it eludes this. And it's not clear how to make compact subproblems for some of these stat problems. We can't quite find, so far, the structure. With the DP problems, it was often on a line, so you kind of know you go from left to right, or like you're working your way in, or there's some splitting in half, right? There's a clear structure, just like binary search, there's a line. You need structure to get good algorithms. And if
We're not good like clause by clause.
can you do it clause by clause?
Satisfying the first I clauses.
So then, okay, so the first clause, you probably have to say, I'm going to satisfy it by choosing one of the two variables. So I'll say first clause was chosen by x1, second clause was chosen by x10. So it feels like for every clause, I have one of two choices as I go from left to right. And so when I'm working on clause 11, I have to remember what I chose for the first 10. But that seems like we're getting a similar situation where I'm getting 2 to the number of clauses. So, I mean, when all these questions are posed as why not or can you, maybe there's more ideas where you can, but the immediate obstacle is that if you just want to throw DP vanilla at it, it's generating too many subproblems. You can save them all, but it's still a huge table. Yeah.
I was gonna say maybe you could make like a table of like the different combinations of like x1, x2, and then x1 bar, x2 bar.
sort of, like mark ones or zeros depending on if it's in the conjunctive only form. And then you can kind of do something with that, like maybe make it into like a graph or something and see if
Oh,
it's a
okay.
cycle.
Okay, good. I think you guys are stumbling into some stuff. So let's get back on the railroad tracks. Okay, so but like this problem without realizing that you have all four clauses, so a little more organically. How, another way to try to figure out this one can't be satisfied is to like presuppose, what if I set x1 to be true? Right? And if x1 was true, then okay, there's two clauses involved, or there's four clauses involving x1, right? But the first clause, what does it tell you about x2? It tells you that x2 has to be what? True. Okay. And then the second clause tells you that x2 has to be right. Okay, so it can't be both. Right. And then same with x1 is false, we'd have these two things. So if x1 is false, then the first clause tells you that x2 has to be true. Wow, some of these questions are so easy, you're embarrassed to answer. But I don't get embarrassed, so I'll just wait. Okay. And then the second one, it says x2 has to be? Okay. Right? So you can at least it feels like some choices force some other choices. Right? Which is something that wasn't true with the 3-sat. Even if you plugged in one thing, you still have two choices left. Yeah, so you have a little bit more of a forcing, sense here that you didn't have before. So, yeah, the word that was suggested was graph. And maybe we can try to make some kind of graph that tries to capture and model this forcing. Yeah?
If we find it true and not true for the same variable,
Yeah. So let's just figure out how to model this. So ultimately, we're going to develop a graph algorithm. Okay? All right, so what would be a natural choice of vertices for this graph? We need vertices and edges, so we can start with vertices.
And a vertex for every variable being true or false. So two vertices per variable.
Yeah, one for x1 and one for x1 bar or something. Yeah, so that's like setting x1 to be true or x1 to be false. Okay? So we'll have a vertex for every, I'll call these literals when it's xi or xi bar. A variable is xi and literal is xi or xi bar. Okay, and what is a reasonable idea for edges? Yeah.
You sort of connect it for like an implication.
Yeah, so if setting x1 to be true forces x5 to be false, maybe I can draw an edge from x1 is true, which is x1 for us too. x5 is false, which is x5. Okay. Is that what we're going to do? Okay, we're going to add. That's right. So if you have A or B, that means if you set A to be false, then B has to be true. So I said I'd draw an edge from A bar to B. And if B is false, then A has to be true to keep things alive. So I'll draw an edge from B bar to A. So it's a little funny looking because A or B actually draws edges with A bar or B bar, because that's how the implications actually work. Okay, good. All right, so same thing. All right, so for example, this would be an implication graph for the formula we know that can't be satisfied. Okay, so we have a lot of edges here. I think I've done it correctly. And I've annotated the edges with the clause that produced it.
You can basically.
Right. So we're going to work up to that. So right. So if I plugged in an assignment like true and false, and that would force false and true or something, right? At some level, what should I look for in the implication graph, relative to fill in the blank? An assignment is satisfying if and only if blank in the implication graph. Yeah.
This isn't formal, but essentially you shouldn't have x1 and x1 bar or any conjugates in the same.
Oh, that's true. Okay, okay, yeah, I'll just get there then. Okay, so first of all, you can't have any true to false in the implication graph, right? That's our definition of, if you set something to be true, then everyone it can go to must be true. Okay, so I just want to first interpret the graph correctly. Okay, good. Right, so that's one. Okay, so I think you guys were getting to this, but on the left we have the implication of graph that's not satisfied. I mean, a formula that's not satisfiable. On the right, something that's satisfiable. Just looking at the graph, what do they seem to have in common or different?
X2 doesn't imply X2 bar in the right graph, and similarly, X1 bar doesn't imply X1.
Yeah, okay, so in this graph, X2 bar can imply stuff for X2. The X2 bar won't imply anything for, right? Now, but in this graph, as I think you guys have said like 5 times, you can go like this, and then like this, and then like this, and then like this. Right? So once you set one of them to be true, they all have to be true. Right? So the directed cycles in this graph, if x1 and x bar are in the same directed cycle, one of them has to be true, right? You have to set x1 to be true or x1 to be false. So either x1 or x1 bar is true. And that starts forcing other things to be true until you get back to its negation. Say that has to be true too. And now you're screwed. Yeah? I mean, that's not the formal term. Whereas down here, it is true that if you set x2 bar to be true, it will force x2 to be true, and that sounds bad. But what can you do instead?
You can set X2 to be true.
Yeah, in particular, you can set x2 bar to be false.
Yes.
And that doesn't imply anything for x2, so that's okay. So they're not in directed cycle. So at the very least, a directed cycle clearly shows it's not satisfiable. It's not obvious that not having a directed cycle implies it's satisfiable, but it is a necessary condition. All right, so that's some ideas.
Yeah, how is X2 bar false not implied? X2 is true.
Because the implication graph is only worried about if the starting point of the edge is true, it forces the destination of and it doesn't say that if the starting point is false, that the destination has to be false. It's only true means true, but it doesn't actually mean false means false. Yeah, so it's asymmetric. Okay. Good. Okay, so we want to show that a two-sat formula is satisfiable if and only if every variable is not in the same strongly connected component of this graph. Okay, so one of the directions is easier than the other. Which one?
Right.
Yeah, okay, so if the formula is satisfiable, then xi or xi are not in the same strongly connected component for any I, which I think we had focused on the contrapositive, so it feels a little bit like the opposite of what we were discussing, right? But if xi and xi are in the same strongly connected component, we know it can't be satisfied, which is actually going from left to right in that statement. Okay. So if f is satisfiable, then for all I, xi and xi bar are not in the same strongly connected. It's a contrapositive. Okay, good. So then the harder direction is suppose that xi and xi bar are not in the same strongly connected component for all I. Right? And so what do we need to do? We need to come up with a satisfying assignment. All right. Any ideas?
Could we calculate the strongly connected components?
Absolutely.
Because if any two, so we can just look at the strongly connected components. If for any I, Xi and XiY are in directed cycles, that means they will lie in the same strongly connected
Yeah.
component. If you find such a strongly connected component such that that is not the case, the variables which are, or not the variables, but yes, the variables or the literals which are within that strongly connected component can be your true assignments, and then everything else is free.
Okay. So first we'll take strongly connected components, and we can first just check this condition.
Or everything else which is reachable from that.
Okay. So, but the algorithm, the first thing you'll do is just compute the strongly connected component. Then just check each strongly connected component if it has Xi or Xi, right? So you can assume all the strongly connected components are kind of good, in the sense that they don't have any of these contradictions inside them.
Yeah.
And then you said, okay, let's take a strongly connected component and set it to be true. But which one? You can't just do any willy-nilly, can you?
You have to find one which cannot reach any of the bad ones.
There are no bad ones. All the strongly connected, well, I don't know how you define good and bad, but here I was defining good as it only has one of the Xi or Xi bar in it. Yeah.
It's a source SCC.
Okay. Yeah. Okay. Let's go a little slower. Okay. So in this strongly connected component, all literals must have blank assignment.
True.
Same. Okay. Okay. It could be false. Okay. So, right. So one thing I'm going to study the graph a little bit more. So one thing is that there's always this complementarity, right? So if I look at an arc A to B, right, then there's always going to be an arc from not B to not A. Just by the way that these edges are constructed. Like it's up in the top right? So every edge we add sort of has this like evil twin edge, right? Opposite direction between the opposite vertices.
The contrapposite trees.
Yes, I think. Yeah. Okay. And so in this graph, a vertex X can reach Y if and only if Y bar can reach X. So there's a lot of like duality and symmetry in this particular graph. Okay. So that also now extends to the strongly connected components. Every strongly connected component has an evil twin strongly connected component, which is going to have the negated variables in the opposite direction. Maybe it's a contrapositive strongly connected component, but I'm only mildly sure. For now, the evil twin strongly connected component. Okay. For some reason, same slide twice. Okay. So, okay, does that help maybe articulate a strategy? Yeah.
Wait, you only have two SCCs then because X has to be part of one and one X has to be part of one.
So the question is, can you only have two SCCs? That doesn't necessarily seem to be true. I can have an SCC to another SCC. Why would there only be two SCCs?
Because you have a vertex for X, you have a vertex for not X.
Yeah.
And unless they're both their own SCC, assuming some SCC, there'll be only two big ones.
No, not necessarily. They just have to be in two separate. So there's at least two. Remember, the number of variables is like unbounded. You can have like, we're not unbounded, but like, it's not very many variables.
Yeah.
Yeah, at first I'm not sure why we would be too concerned about having giants. I mean, it's quite possible that A can reach B, but B does not reach A, right? All over the place. So we can have something like this. I don't know, have three components going down and three components going back. And then there will be like some correspondence based on the symmetry. Like these will be evil twins, and evil twins with each other. That could be possible for three different strongly connected components.
So are we trying to find an SCC such that it cannot reach its evil twin?
No.
Yeah.
Okay, so at some level, you want to pick one SCC and make it either true or false. Right? I mean, at some level, that's what we have to do. We have to go one SCC at a time. Which is like the safest, and why? Like, because we know that same SCCs have to be given the same assignment. One SCC, everyone gets the same assignment, right? So we're gonna have some algorithm of the form pick this SCC for some reason, good reason, and assign everyone either true or assign everyone false. That seems like any algorithm we come up with is going to probably follow this framework, just doing one strongly connected component at a time. But you want one strongly connected component. Maybe you could make a mistake or something, right? But maybe there's a choice of SCC that's very conservative and very safe. Yeah.
Why can't you just pair up all the components and assign in each pair, assign one of them to be true and the other one to be false?
How do you know that's going to work out?
Because there's only
It's like each one won't interfere with its pair.
But you could have like the pairs getting crossed up. It's quite possible that there's one-way implications too, right?
Oh.
We just know that they're not the same strongly connected component, but maybe xi to be true does force xi bar to be true or something, which would be that. So you can't set xi to be true. So if you're going to pick a strongly connected component, what's the most conservative, safest choice, and why? Yeah.
I got a question.
Okay.
Is it guaranteed that the graph is short?
No. Yeah, this picture might be misleading. Doesn't have to be
You
disjoint.
have an SCC where xi is true, and then that SCC has an output way to a component where xi is false.
Yeah, sure, that's possible.
Like, what does that mean?
That actually showed up in our example. So the question is, so in this there's no SCCs in our formula that was satisfiable. So they're all on their own. And here x2 bar can reach x2.
why are they all on their sheet x1 bar and x2 together?
Are they actually?
Yeah, there's a second.
Oh, okay. So there is an SCC.
And there's like the
Oh, okay. Sorry. There's two SCCs. Yeah. And one of these can actually reach the other. So I'll do this one in purple. Purple can actually reach yellow. Yellow cannot reach purple. And there's no contradiction. There's nothing special about it. It just says that if you set purple to be true, then yellow would have to be true. If you set yellow to be true, that does not force purple to be true. Yeah.
Can you topos sort that?
Yeah, you can topologically sort. That's easy. So
Isn't that a conservative choice?
which one?
When we topos sort.
Yeah, you topo sort and then, yeah.
The first one, you can use
The what?
the SCC with like, collapsing
the same.
A source? So, sorry? Yeah?
Sync. You should do it for sync because it doesn't affect any of the other ones.
Okay, so if you choose a sync, another nice thing is that C bar is always a source. Yeah. And so setting the sync to be true doesn't force anything upon anyone. Also, setting a source to be false doesn't force anything to be everyone. If you actually set the sync to be false, then that forces everything upstream to be false because it couldn't be true. There's always been this opposite thing going on. So if you set a source to be false, true, false, if you set the source to be false and the sync to be true, you're not imposing anything on the rest of the graph. So that's a free assignment that's not going to create any problems for you. It doesn't imply anything else. So you can always do this.
Then you can remove this source in the sync and then assign the next sync to be true and so on.
Yeah. So you can peel off one source sync pair, the sync and its evil twin source. You remove it. And what remains is the SCC of the remaining formula implications. And you just keep going. You keep going. Okay, so yeah, assigning syncs to be true, sources to be false is worry-free. No implications. Good. So that's I guess the algorithm. Again, it always looks more complicated than it is, right? But you just take the SEC, the implication graph, and once you've kind of carefully studied the implication graph and thought about a couple of these extra observations, it falls out very nicely. Okay? What will be the running time of our algorithm?
M plus n.
Yeah, m plus n. So strongly connected components is quite fast, right? M plus n. And then just checking the strongly connected components is going to be pretty fast. It'll be like ON or something. And now you just start processing things in, reverse topology, sync first, assign all to be true and just false. Yeah, I think this won't be hard to do in linear time. Okay. All right, good. So not only can you solve 2SAT, but you can solve it as fast as you could possibly expect to. Okay. All right, good. Good. All right. Okay, I'll have to do some video editing. All right. Which only takes me way longer than it should, but that's another story. All right. So we've done 2SAT. Let's do max 2SAT now. Okay. Same problem as before, except you're trying to satisfy as many clauses as possible. Okay. So given that we got an algorithm for 2SAT, I was going to see if I'm going to take another vote again. Okay. So first of all, who's not voting? Okay. This is like the greatest class ever. All right. So now for max 2SAT, you either say it's hard or maybe now you think it's easy or something, right? Okay. Who still thinks it's going to be hard? Still everyone. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that was the peer pressure one at the end. Okay. And then, oh no, did I get that wrong? Okay. And then who thinks we're going to get an algorithm? Okay, 2. So actually, somehow it got worse. Did it get worse? Oh yeah, although 2 people died. That's also a problem. Uh, oh no, okay, it's gotten a little bit better. Oh, we add someone? Oh, okay. Okay, so we're adding people to the class. That means the lecture must be going very well. Okay. Okay, so it did get a little better. That's at least the right direction. Okay, so we're first going to focus on max less than equal to SAT, for reasons I'll make clear, but it's a little easier, basically. Okay? And we are actually going to show it's hard. Okay? And so how are we going to show it's hard? What's the high level proof setup? How do you show that max 2 SAT is hard? Yeah, so mechanically, what are the steps? What does that look like? What does reduce mean? Yeah, just in simple terms for this problem. Yeah. Yeah, so particularly we want to take some problem, like we're going to do 3 SAT today, and turn it into a max less than equal to SAT in polynomial time, like you said, feed it into the black box, which is going to return some kind of answer. In particular, it's not going to return a yes/no answer, right? Because before we were doing yes/no questions, this is going to return some quantity. And then we're going to have to take a little more effort to try to interpret that quantity back to the yes/no answer we're interested in. Okay, so slight mismatch in output type. So that's one thing to keep in mind. All right. Okay, good. So what we want to do is take our conjunctive, our 3 SAT formula, and convert it into something with at most 2 variables. How? Yeah. Okay, so I have A or B or C, and then I'm going to convert it into A, B, C. 3 different ones. Oh, A or B and A or C and B or C. B or C, right? But why are you shaking your head?
That's a word like A is
Okay, sure. Well, I also, yeah. So first there's an issue of, okay, so first of all, with max 2 sat, it's not like as much an and as much as like almost like commas in between because you're trying to get as many as possible. And okay, so when the idea was like, well, if only A is true, you're only going to get 2 out of 3. So A gets converted to 2 points, which itself is not a major issue. But if you did A and B were set to true, you'd be getting 3 points, right? So if we did this across the board, then it'll be a little bit so let's say you did this across the board. So you started with your formula and you turned it into your new formula along with this, right? And let's say you originally had m clauses, okay? And this gets turned into, I guess, 3m clauses because we took each triple and turned it into these 3 pairs, right? Okay. And then let's say you put this into your black box for 2 sat or at most 2 sat. And suppose it returned, so first of all, if it returned 3m, then actually I think the answer is that means the formula was satisfiable or something, right? There are some cases it might be good. But if it returned 2m, right, it just says, oh, 2m clauses in your new formula could be satisfied. It's not clear if that means that the original formula can be satisfied or not. It's true that a satisfying assignment to your original formula will satisfy at least 2m clauses in your new formula, but it's not clear that an assignment satisfying 2m clauses in your new formula is going to satisfy all the clauses in your original one, because maybe you're getting 3 points from a bunch of them that makes up for getting 0 points for some others. So it's tricky. Any other? This is the right direction. The ultimate solution is quite tricky.
you would preserve the value of A or B or C.
Can we preserve the value of A or B or C?
Fourth variable.
Yeah, I don't know. Yeah, so certainly there's lots of options. Like, can we introduce auxiliary variables, make some like, kind of gadgets? Yeah, there's definitely a big, you can do whatever you want, really, right? So, yeah.
So the idea is that you
Something you can work with really numerically. I mean, this is a little trickier than before because we're going from yes, no to some quantity. And yeah, so something like that. Oh, the only way to get 5 points is if they're all true. Otherwise, it has to be less or something. But something, sharper than this, basically. Numerically sharper, I guess. Quantitatively sharper. There was another hand, maybe.
consider it
Oh, so another thing is, okay, so technically the black box just gives you numbers, but suppose it gave you the assignment, which if it gives you numbers, you can figure out the assignment by the same thing we did at the beginning of class. So let's say it gave you the assignment, and suppose this assignment didn't satisfy F. Can you conclude that F is not satisfiable? Not necessarily. So G wasn't trying to satisfy F. G was just, the black box wasn't trying to satisfy F. It was just trying to maximize the clauses in G. And maybe the thing that maximizes the clauses actually doesn't satisfy F, even though F is satisfiable. Like maybe it returns 2m plus 10. There's a satisfying solution that can get you 2m clauses in G, but there's an unsatisfying solution to F that can get you even more clauses in G just because it's getting a lot of 3 points at a time instead of 2. So even that is not so clear. Yeah, so we don't have as much control as the black box. We can't kind of control the intention so easily. Yeah.
So you have here the clause of the so that I'm gonna sound the other.
Yeah, I don't know what to say about or I guess you said some kind of clever thing. Okay, it's hard to rule out a suggestion as broad as something clever. Um, uh, yeah, but okay, but yeah, it's not clear that it seems like maybe you could do something clever. It's hard to rule out doing something clever, right? Maybe we can add more clauses, like play around with A or not B to try to like, oh, okay, the bad case for us is like, okay, we can't tell apart when you're getting 3 points or 2 points or something, right? Can we do something to fix the math? Add more clauses or something. Yeah. Okay, so I think what we're going to end up doing is sort of similar, but quite more elaborate. Okay, so given a clause like A or B or C, look at these 10 clauses. Okay, I have a clause for A, B, and C. I also introduce a new variable y. I introduce a new variable y and I create 10 clauses. The first 3 are A, B, and C just separately on their own. And the next are things like not A or not B, not B or not C, and not C or not A. Okay, and then the last family is y, A or not Y, B or not Y, and C or not Y. Okay. So this is a little bit eccentric. But what we're going to do is we're going to start tallying these things up. Okay. And actually, I think once you see the first 2 rows, it'll make a little more clear why we're putting in Y. Okay. Because it's clear that the Y is put in there to try to fix the first 2 rows. Okay. So I have basically the 3 basic assignments because the other, under symmetry. And we're just going to say, okay, so say like A, B, C, those 3 clauses. If my assignments were false, 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 how many points would you get? It's not a trick question, but we're just going to go through it, okay? So the first one, false, false, false. How many points would A, B, C get? 0. Okay, true, false, false. True, true, false. And true, true, true. All right, the next one takes a little more effort. So you're looking at not all these knots, pairs of knots. All right, so false, false, false. True, false, false. True, true, false. True, true, true. Okay, so if we tentatively start adding things up, false, false, false gets 3. True, false, false gets 4. True, true, false gets 4. And true, true, true gets 3. First of all, you probably want the things with at least one true to get more points than the things than false, 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 right? So if you look at the last row, yeah, okay, well, let's just go through it. So the black box is going to try to maximize the amount of satisfying assignments, right? So it's going to choose the Y that maximizes. So once you plug in for A, B, C, then you put in the best Y. Yeah, okay. So that last row, false, false, false. You get 3 points. Okay. True, false, false. 3. Okay, true, true, false. And then true, true, true. You can get 4 by setting Y to be true. Yeah. And now you start adding these things up, and you get exactly the separation you wanted. Okay. So false, false, false only gets 6 points. all three other configurations which would satisfy A or B or C gets 7. And now there's like no ambiguity. It's just 7 or 6. Yeah, and so now you can start working with this. Okay, so good. Right, so I don't know, that's just formalizing it. But the point is that given one of these three SAT clauses, you can come up with a very clever combination of 10 clauses so that if the formula is satisfied, you can get 7 points. If it's not satisfied, you can only get 6. Okay, so that's how we're going to create our 2-SAT formula. We're going to use this gadget. Okay. Okay. So, right. Okay, so now we still need to do, I mean, it looks like we're off in going in a better direction, but we still need to finish the analysis, right? So I want to show if G is satisfiable, you can get a certain number of clauses, and then we need to show if you can get a certain number of clauses in G, then F is satisfiable. Okay. So suppose F is satisfiable, how many points can you get in G? Yeah, so okay, we're doing M clauses. I don't think I made that clear earlier. So M clauses, and you can get 7 points for each, right? So your satisfying assignment, whatever it is, you just first move that exactly to G, and all that's left is choosing Y for each of the clauses. And based on our table, you're always in one of these three columns because you're satisfying the thing, so you can get 7 for every single one. Okay. So then you get 7M. Yeah. Okay. And then what if F is not satisfiable? Yeah, you can only get at most 7M. Each clause can only get you 7, but for any in particular, if you got 7M, right, you can only get 7 from every clause in your new formula. So in every clause, you're getting 7, which means that in every clause, you're in one of the three good columns, which means that the underlying variables for the original one must satisfy the original clause. Okay, good. So I won't write it out, but that's the idea. Good. And okay, so that completes our reduction, right? So not only do we describe it, but in the last part, I didn't, of course, write it out in full, but we did the if and only if. So you need to make sure when you do a reduction that you show that yes means yes and no means no in both directions. And it's quite common to accidentally do the same direction twice by accident, so just keep that in mind. But you'll get better as you practice. Okay, good, good. All right, so now we can do less than equal to SAT, and now we just have to adjust that and make that work for 2-SAT. Okay, and now that we've already shown that less than equal to SAT is hard as 3-SAT, we can just reduce from that. So I can take an instance of less than equal to SAT, try to turn it into an instance with exactly 2 variables each, plug it into a black box for 2 variables each, and return it. Yeah. Okay. Any ideas? So the only issue is that some clauses have 1 variable. Yeah. Yeah, we did this the other day. Right, so how do we convert a singleton clause to 2 variables? Yeah, I'll just add some variable y. And I have a or y, a or not y. You can only get one of them, no matter what. Good. Some reason I have that twice. So that's it. We just add those extra variables like we did the other day. And I mean, I guess maybe the one thing to point out is that you do a minus k. You do a minus k? No, you don't do. You just return the same number, right? The quantity doesn't change. I think that minus k is a typo. Sorry, let me explain. So you take your formula, it has some singleton clauses. You do this trick, y or y bar for each one, and then you plug it into your black box. You get some quantity. So you can satisfy 100 clauses. And then now you want to say how many clauses in that original input. But it's the same number, right? Because the singletons. Oh yeah. If you satisfy, then you get both no matter why. Oh yeah. Okay, that's right. That's right. Okay, good. I should have done that more slowly. Oh, there was something here. Okay. This is where we do it. Okay. So if you're satisfying P clauses in F, then once you had the variables, you're going to get an extra K. Okay. Good. Good. Okay. Good. So you subtract K and then you get the right quantity. Okay. So that's it for the what was on the material. I loaded up some problems to get a little practice. I'm not sure how excited you are about the practice, given it's not on the midterm, but it was a natural thing uh, to put. So we have about 10 minutes left. Is that okay? Okay. All right. So this one actually goes back a class. Okay. Uh, but here's sort of a classic problem. Okay. So it's about what's the difference between k sat and k plus 1 for larger k. We just did the case k equals 2. Some funny stuff happens. Yeah. Oh, I should maybe put a concluding note. I do want to emphasize that 2sat and max 2sat did not look so different, obviously, right? But they had remarkably different characteristics. 2sat had a very, very fast and pretty clean in hindsight algorithm. You have to be pretty clever. And max 2sat turned out to be just as general as 3sat. Somehow it feels like that max gave you that extra half a degree of freedom where suddenly it wasn't as straightforward as an implication graph. Right? If you think about the 2sat algorithm, it's saying like, oh, this is force, this is force, this is force. You have to do this. There's no other options, and that's how you pull out a solution. Somehow max 2sat, because you can choose to satisfy a clause or not, suddenly more choices are coming in, and suddenly you can't deduce things quite so easily. Yeah, so that like hair, it seems like a small difference, but they're complete opposite problems from an algorithmic standpoint. Yeah, so we're going to have more examples like this, and trying to understand this distinction between the problems we can solve and the problems we can't solve is quite subtle and quite important. Yeah, a lot of the problems we can't solve are actually quite natural and would be quite useful, and we still try to do heuristics anyway because they're so useful. But we have trouble getting guarantees like the kind of guarantees we got for Dijkstra's algorithm or strongly connected components. One of these, no matter the input, I can get this for you in a certain amount of time. It seems like very hard to capture some very useful problems. Okay, so just something to keep in mind, and we'll keep exploring this theme after you forget it all as you study for the midterm. But yeah. Okay. Yeah. Because okay, so why did we start with a 3sat instance and turn it into at most 2sat? Because in that problem we already knew 3sat was hard, and I wanted to show that at most 2sat is probably hard too. So how could so hard to solve? And the way we're claiming that things are hard to solve is because solving them would solve something else that's too good to be true. Like starting with just Boolean formulas. If you could solve Boolean formulas, maybe you could cure cancer. Maybe that's too good to be true, or whatever. It just seems like solving Boolean formulas is so general. And then 3sat, why is it hard? Well, if you solve 3sat, you can solve Boolean formulas and then you can cure cancer. Okay, that seems too good to be true. Not that we won't cure cancer someday, but and then less than equal 2sat, max less than equal 2sat, it doesn't seem that different than 2sat. Yeah, even though most of you still voted that it was going to be hard, probably because you knew I was going to zigzag. But but still, to demonstrate it's hard, it should be able to solve something already accepted as hard. Oh, if you solved one of them, that would be fantastic. Yeah, if you had an algorithm for 3sat or less than equal 2sat, that would be great. And then all of these things would collapse. If you solve less than equal 2sat, you would get an algorithm for 3sat, and you would get an algorithm for. So what's going on? We get stuck in a situation We can't come up with an algorithm no matter how simple the problem sounds. 3-SAT sounds like a simple problem. It doesn't sound that much more complicated than strongly connected. It certainly doesn't sound that much more complicated than 2-SAT. Imagine I presented 2-SAT first, right? But you're stuck. You spend 20 years on 3-SAT, you can't make progress. So what do? You presuppose, what if I had an algorithm for 3-SAT? You know, oh, that would actually imply this. That would actually imply that. Oh, that explains why I couldn't come up with an algorithm. Yeah.
So they definitively
Are there any problems that definitively show you can't do polynomial? Um, okay, there's some like weird counting problems. Like if I wanted to count the total number of distinct paths from S to T, just counting can take a long time because the answer is a large number. So there's some eccentric problems like that. If I'm just focusing, if I restrict myself to search problems, which I'm going to define as you're looking for some kind of object that you can recognize in polynomial time, at least problems that you can check the answer in polynomial time, right? If I just restrict myself to the class of problems where there's two issues, right? There's one, can you find the answer? And two, can you even check an answer is correct? So let's look at the problems where you can at least check the answer is correct. And the question is whether they have an algorithm to find an answer, right? I'll call those search problems. We don't know if search problems can be solved in polynomial time. There are no search problems in that definition of search that have been shown to not be solved in polynomial time. That definitely require exponential time. And then we'll actually be able to, I'll be able to explain, in a month. Yeah.
So even in like the first few classes, we showed that
Yeah.
can't do that.
Yeah. And log in.
But like there are source. So is that
Well, okay. So if you don't assume restriction, that's just going to make it harder to get a lower bound, right? Well, okay. So the question, well, I think in general, there's always some kind of gradient where you have some model with certain restrictions, and you can always remove more and say, do you still have a lower bound? Remove more, still have a lower bound. And then there's some level at which we have a lower bound, and then you remove some, and suddenly we don't have anything to work with. So right now, we don't know how to do this. But I don't know if you're even to say that there's no restrictions is even unclear because you're still working on a computer which imposes some restrictions because it has to do sequential operations, things like this. So I'm not quite sure if the question is super well posed. But certainly, yeah, the comparisons is just something to get some kind of hook. And then, maybe don't take the word lower bound. I mean, it still tells you something about the nature of the problem, right? And it kind of gives some justification for the merge sort. And there are situations you're comparing names alphabetically or something where this makes more sense. Yeah.
With the max 2-SAT thing, can't we graph that we made and try to like figure out the middle?
Yeah, okay. So that's worth reflecting on. How come we can't use our 2-SAT algorithm, as beautiful as it is, some way to get a pretty good max 2-SAT algorithm, right? I don't know, if you studied the implication graph, wouldn't it still tell you something? But for example, since you don't have to satisfy all of them, xi and xi bar might be in the same component. I don't know. What do you do? Maybe you could do something sensible, but some of the things we got used to in pure 2-SAT world has certainly changed on us. Maybe they're all in the same strongly connected component. So the implication is only because if I set this to be true and I have to satisfy this clause, I have to set the next thing to be true. But if you don't have to, then so it's like you could include this edge, you might not want to include this edge. Yeah, maybe that gets to your point about cuts and stuff, but but also cutting one edge. So in fact, that tells you that there should be some kind of problem related to, I give you a graph and can you find certain cuts with certain properties so that it gives you basically an implication graph. That should be also hard to solve because then they would be able to solve max two set. Will be sort of the opposite side of the coin. But yeah, maybe it's worth pondering. How do we get so close and yet not get the whole thing? Related with the implication graph? I should think about what the best algorithm for max two set is. I actually don't fully remember what the best algorithm. But certainly three sat is not doing that. Well, there's no implication graph for three sat. So yeah. If you got a 1/2 approximation, it doesn't tell you about three sat. It doesn't tell. Yeah. Well, there may be some limit because of this PCP theorem, right? Like if you do better than 7/8 for three sat, then you actually get the whole thing. But that's very deep. Okay. Okay, maybe you guys didn't want to solve this problem. I'll at least describe it because it's a natural exercise that we always do, and we might not put it on the homework this year in favor of another problem, but it's still worth thinking about. So this problem is going from k sat to k plus one sat and going from k plus one sat to k sat. Yeah. So actually, I think one of the directions you might be very comfortable with. We've kind of done it several times. Yeah. It's like going from k plus one to k. You can convert from k to k plus 1 very easy. So it's easy to show that k plus 1 is at least as hard as k. How do you convert from k to k plus 1? You can do that adding the y and not y and duplicating. So one direction's easy. The other direction's a little bit trickier because you have a bigger clause and you're trying to turn it into two smaller clauses. Yeah. So that's usually it's a two-part question where I put the easier one first as a warm-up and then the second one is worth thinking about. But this is a very yeah, so if you want to think about it on your walk home in the snow. Probably don't. Okay, so we'll end there and then we'll do some kind of review sort of thing on Tuesday. And I also have office hours on Tuesday and all that. Yeah, and I guess we'll try to remember to bring pens because we think that this whiteboard thing would be more fun than sitting. But maybe it's not. Maybe it's tacky. Who knows? Okay. Yeah. Well, yeah, I mean, you know how to go. I mean, it is true that you know that you can go from k plus 1 to Boolean formula to 3 sat back up to k, but that's lame. Try to do it directly. Yeah, yeah, try to do it directly for the sake of exercise. Yeah. All right. Have a nice weekend.